Okay, good morning all of you. My screen is visible.
Yes, sir.
Okay. So today we'll see the effect of source inductance and three-phase fully controlled converter. So normally, whatever we discussed so far, let considered source is not having as a impedance or a inductance. But practically speaking, there is a inductance or let it be as a resistance, so that things will be available. If you are not considering the source effect, then what will happen, whatever output you are getting, that is not exact value. That's what when we are doing theoretical and practical calculations in a lab also, there is a slight variations will be there because of the these conditions. Now, in the previous version, means while I am explaining the semi converter and full converter and all, I didn't show this LS. Whatever it is there in the diagram, so this simply I mentioned like this, means I'm not taken into count in this inductance. But strictly speaking, there is a inductance also available. And another thing we discussed in the previous classes and all, the sequence, whatever sequence I mentioned, whether it is a 6, 1, 1, 2 and so on. Just a minute. Now, here generally there is a 6, 1, 1, 2 or 1, 2 it will start anyway based on the alpha, and then 2, 3, 3, 4, 4, 5, 5, 6, then again 6, 1. So this is the normal order, whatever we are represented in the previous one. So this is the order of the conduction. So by seeing this order, we can notice one thing. Suppose anywhere if we observe 1, 2 and then 2, 3. What is meaning of this? 60 degrees, thyristor 1 and 2 is conducting. After 60 degrees means another 60 degrees, then 2 and 3 will conduct. Means one is upper, another one is lower group divide. Again 3, 4. So from this, what is observation? 1 is conducting, 2 also conducting. After 60 degrees, 1 is going to turn off and 3 is going to turn on. This is the sequence. That instant we assumed that source is not having as impedance or inductance. Immediately after 60 degrees, 1 is going to be turned off completely and 3 is going to turn on completely. That is what we discussed so far. But 1 and 3, we can see that 1 is carry the current during this instant 60 degrees. Completely it carries the load current because current is passing through T1 and then it goes to the load. So whatever load current is there, that current carried by the thyristor 1. Immediately after 60 degrees, we are giving firing pulse to the thyristor 3. Thyristor 3 will carry the load current instead of thyristor 1. That is instantaneously it will changes from thyristor 1 to thyristor 3. But if source is having some impedance or let it be as inductance LS, immediately whatever current is passing through the thyristor 1 should not reaches to the 0. It will not reaches to the 0 immediately. And also thyristor T3 will not carry the total load current directly. There is a some time is required to turn off the thyristor T1 and similarly gradually thyristor T3 will carry the load current. Let see any instant this current is a load current, some magnitude carried by the thyristor 1. Similarly, up to 60 degrees, let it be, this is a 60-degree instant. Up to that it is carry the thyristor 1. According to previous analysis, T3 is going to fire at 60 degrees means this current will be 0, and then this current carry by the T3 immediately. This is going to be 0 and then this is carry the T3 current. But normally current, whatever current it is carried by the T1, it will not suddenly turn off to the 0 value, or suddenly it will not reach us to the 0 value because of the source inductance. What will happen? This current will be gradually decreasing, and from this 60-degree onwards we are firing the thyristor T3. This current will be gradually rising. And now we can notice during this instant, what is the observation? There is a current at 60 degrees, T1 current is present, some duration. Let it be this duration, from here to here is some duration. Yeah, this gap, we noticed that T1 current also available. This is a T3 current, and from 60 onwards T3 current also available. Let it be, this is a 60. Now, so what is the observation is T1 is there the current, as well as the T3 also having the some current. So both devices T1 and T3 have some current. Then what will happen? T1 and T3 will together fire during this instant. Whatever the overlap means, both having some current, this overlap I call it as a mu. That is in the upper group side. As usual, in the lower group, device will be remains conducting, because it will not overlap with some other, because it is in the both instants, here 2 is there, here 2 is there, same, that's the reason same device. So then in between, in this we can see that in between there is a one more interval come into the picture. What is this interval? It is changing 1 to 3, then 1, 2, 3. Three devices will conduct in between during overlap condition. This overlap condition, all the three devices is going to fire. After overlap period, what is else? 3 is completely on, as usual 2 will be remains there. So then 2, 3 will come into the picture. So in every interval, there is in between one more interval come into the picture if I consider as a source inductance. That is the different. I will show that previous one without having source inductance, now with having source inductance, and I will explain one more time. You can see that this is the instant without having source inductance. So let consider the inductance effect is not considered. This is a without overlap or without inductance. So then what will happen? This is the supply voltage. These are the crossovers, as you know that 1, 3, 5, 4, 6, 2 in the lower side. There is a negative, more negative. C device is T2, and this is a phase device is T4, and B phase device is T6. This is the overlap period. Now under this instant, now we can see the sequence is very clear. What I consider is without considering as a source inductance. In that, the device conductions you can see. Suppose if we start at this point, what is the sequence? Let it be 5, 6. See that. So this is a 5 and 6 is conducting in during this, because 6 is there throughout this duration, 1 is there throughout this duration, and again 2. Whatever the boxes are there, firing pulse will be available. Now, so in the first instant 0 to 30 degree with respect to omega t, in this box, what are the devices is conducting? 5 and 6. Then in this box, 6 and 1. Then next box, 1 and again you can see that 6, 1, and here also 6 1 because it is a 60 degrees conduction up to these two boxes, 6 1 only conducting. Then after that what will happen? 1 and 2. Again here also 1 and 2. Then 2 and 3. Then 3 4 because each will be as a 60 degrees. Then 4 5 and 5 6. Again 6 5 6 and cycle will be repeated from here onwards. Anyhow 4 5 then 5 6 6 1. So now we can see 1 2 3 4 5 6. So 6 pulses will conduct during this instant without having as an overlap period. So now in this observation you can see that 5 and 1 there is the here what will happen, 5 is going to be turn off, 1 is going to be turn on. Similarly in lower side you can see that 6 and 2, 6 is going to be turn off, 2 is going to turn on. Similarly in upper side every instant one is a upper group, another one is a lower group. We can see that there is a changeover. So one see that the crossovers, wherever crossovers are there, there is a changeover, depends upon the availability of the firing pulse. And again 2 4 changeover, then what will happen, 3 5 changeover, then 5 1 changeover, like this. So in every instant if I consider as a source inductance, there is a overlap also come into the picture. So in between these device should not turn off completely and should not turn on completely. That's why between this some instant both devices is going to be fired. And again here some the duration is decided by the inductor value and firing angle and all. If large inductor, this gap will be more, means overlap period will be more. Like this it will be there. If I consider as a overlap the shaded portion, what will happen, there is a other side, mean this device and this device, both devices is going to be fired at that shaded portion. And here also you can see both devices are going to fire. So this is the instant we can notice that a thyristor outgoing device and incoming device together will fire some duration, that we call it as a overlap. That will be takes place because of the source inductance. Source will not allow to change suddenly from rated value or carrying the load current to zero value, and that gradually decreases from rated value to the zero or load current to zero, and immediately other devices also suddenly from 0 to rated it will not take, and gradually it will build up the current. So this is the case of without overlap case. 6 1 1 2 2 3 3 4 4 5 5 6 and then 6 1, that is the sequence. But actually if I consider as a source effect, in between there is a one more interval is going to be come into the picture. So now we can see that this is what I explained. Suppose 6 1, then 1 2, then 2 3. In between, now tell me in between what is the interval will come into the picture, like that all the cases. So by seeing this it is very clear. 6 1 and 1 2. What is common? 1 is common. So therefore 1 will be remains there for the device, because changeover is not from the upper group. Now here changeover is in the lower group. 6 is going to turn off and 1 is going to turn, 2 is going to turn on. Then what will happen? This interval will be 6 1 2 will come into the picture. Now and here what will happen? 1 2, then 2 3. 2 will be common both sides. Then what is 1 also turn on, 3 also turn on some interval. And then after 2 3, what is next interval? Then 3 4. Then in between 3 will be remains, and then what is changeover? Then 2 3 4, like this. Then 3 4, after that 4 5 normally, and now in between there is interval 3 4 5. Now this is the order of the sequence. Now if I consider as a source inductance, you can see that 6 1, after that 6 1 2, then 1 2, then after that 1, 2, 3, then 2, 3, then 2, 3, 4, then 3, 4, then 3, 4, 5, then 4, 5, then what will happen after 4 5, then 5 6 normally, but in between what will happen, 4 5 6 is another interval, then 5 6, then after 5 6 is a 6 1, so that will be in between there is another interval 5 6 1, and then 6 1 cycle is going to be repeated. So this is the new order if I consider as a what will happen, source inductance. So that we'll see now. Now we can see that effect of source inductance. The first instant, this one overlap period is 0, alpha is 0 and overlap period is 0. This is same as the previous slide what I showed, this one. So 5 6 6 1 1 2 2 3 and so on. So this is the case, upper group positive group device and then negative group device. So these are the device conductions because 1 3 5 4 6 2 we made it, and now this is the actual thing if source is not having impedance or negligible, or you can say that there is assumption that source is not having impedance, and that condition if I put alpha is equal to 0, these are the device sequence conductions. Now later on, what I consider same alpha is 0, but I consider overlap angle. So some period overlap is there. When overlap will come into the picture? Whenever if we consider as a source inductance. Under that condition, what is observation? See that 5 and 1 changeover. So wherever line is there, that means here see that crossover point, because alpha is 0, automatically crossover instant will be there. So every crossover, whether it is upper or a lower, there is a changeover is going to be takes place at alpha is equal to 0 instant. Or if alpha is some other angle also, at that point there is a changeover will be there. Instead of crossover, from that you count the 30 degrees, there changeover is going to be takes place like that. Now for easy understanding, I made it alpha is equal to 0. Then automatically we can notice that 5, after that 1. What is meaning here? 5 is going to turn off and 1 is going to turn on. That's why I made some shaded portion here. So that portion both is going to 5. 5 is going to conduct and 1 also conduct. So that means 5 already conducting state. Now 1 changeover. So you can see the current waveform also. 5 carry the load current. Then immediately at this line we are giving fire impulse to the T1. That's why what will happen? T1 thyristor is starts conducting. That's why this current from 0 onwards gradually rising, and this current from rated onwards gradually decreasing. Finally, one stage comes, what will happen? Both devices together will fire. So that is the reason we can see that here shaded portion 5 and 1. But what about the 6? 6 is lower group. Lower group it is remains in the more negative only. That's why that will be remains in the T6 will conduct, and from this point onwards T2 will conduct, but here is a more negative, that means B phase is more negative, that's why T6 will be remains there. So then totally how many devices is conducting? From here the instant is 5 and 6, then the changeover is this duration. Under that condition you can see that 5 6 1 is conducting. After that, after overlap period is over, that means what? This instant, at this instant 5 is completely turned off, because that wave current is reaches to the 0, and then 1 current is reaches to the maximum. Then what is meaning? After this period, after the overlap period, this 5 is completely turned off, 1 only will be turned on. Then what about this portion? T6 will be there remains. Then during this instant 6 and 1 only will conduct. After that, what is happening in the lower group? Because here you can see that whatever shaded portion, that is a overlap periods. And now after this instant, lower group is going to be changeover. What is lower group? 6 at this point. 6 is already conducting. Now here I am giving pulse to the T2. So that's why transferring change transferred from 6 to 2. That's why in the lower group current waveform you can see that carry the I6 current and then there is a changeover in this point, then this current will be gradually decreasing and then the thyristor T2 current will be gradually increasing. During this overlap period, both devices will be conducting and positive group device 1 is already conducting state, therefore 6, 1, 2 will conduct. After overlap, what will happen? 6 device will be completely turn off and 2 device will be completely turn on. That's why only upper side is still 1 is positive group device will be remains, therefore only 1 and 2 will conduct. So this is the way we can able to conduct. Now we can see the sequence. Every instant there is a one overlap period is going to takes place. Earlier 5 6 then 6 1 only, but now in between 5 6 and 6 1 in between there is a one interval 5 6 1, again 6 1 then 1 2, in between there is a 6 1 2, like that. So every changeover, one side you can see that crossovers, one is upper side, another one is a lower, next upper, next lower, like that. Every instant or every 60 degrees in between there is a one overlap period is going to take place. Because of that overlap, because either it is in the upper side or it is in the lower side, there is a average is going to be reduced. There is a overlap, the average of this will give as a output. Instead of directly we are getting the output, now the overlap period, two devices will be either in the upper or in the lower. We are reducing the output voltage. Where we observed in the single phase case also, if overlap takes place, incoming device and outgoing 1 and 2 is conducting later than 2 3. So all the 4 devices are conducting. Therefore, what will happen? Your output will be 0 during that overlap. That's why your output is going to be reduces. In a single phase, you can see that average output voltage VDC normal without overlap case 2 Vm by pi into cos alpha. This is for single phase without overlap or without source inductance. Now, in a case of overlap, means with source effect, then your output VDC is equal to 2 Vm by pi into cos alpha minus omega Ls by pi into Id. This is the case of source effect. So now this is the drop. Something before we are getting this 2 Vm by pi, but due to source effect we are getting as a omega Ls by pi into Id. And similarly, by seeing this directly, you can able to represent what is your output voltage waveform. By considering the source effect in the three phase. So how many pulse this one? It is a single phase case. It is a two pulse converter. Two pulse converter we are getting omega Ls by pi into Id. I already mentioned in the previous, if it is M pulse converter, then what is your output voltage expression? Suppose if it is a M pulse converter, what is the drop? This is a M by 2 omega Ls by pi into Id. And now it is, suppose M is equal to 6 pulse converter. 6 by 2, that means 3 omega Ls by pi into Id. This is the drop. Now this is our case also, it is a 6 pulse converter. Then before overlap, what is our average voltage? 3 root 3 Vm by pi into cos alpha, continuous mode. So this is the 6 pulse converter average output voltage without overlap. Then with overlap, what I can write? Simply put minus 3 omega Ls by pi into Id over. This is the case of average expression if I consider as a source inductance. Suppose if I consider as a source resistance also, some resistance will be there. Of course, it may be minimum, but still there is a resistance also you want to consider. Then what is the expression VDC? Actual VDC is this one, and the inductor, if I consider, you have to subtract that inductor drop, and if I consider resistance also minus something resistance, source resistance into current, that is the average. Now VDC 3 root 3 Vm by pi into cos alpha minus omega Ls by pi into 3 omega Ls by pi d into Id minus Rs into Id. And if I consider voltage across the thyristor drop also when it is conducting minus Vt, like this is the actual average output voltage if I consider all the parameters. So this is very simple. You can just mention normally supply voltage, and if it is overlap is 0, this is the sequence. Then if I consider overlap, there is a changeover instant, two incoming outgoing together will fire, and while it is conducting or overlap period, 3 devices are conducting, and without overlap period only 2 devices are going to conduct. So like this we can able to represent the waveform and explanation and small derivation as usual only drop. As you know that 3 root 3 Vm by pi into cos alpha is average expression in case of 6 pulse converter, and drop will be how many times we are getting here, 1 2 3 4 5 6, one full cycle 6, then cycle is going to be repeated from here onwards. So one portion if you integrate and multiply by 6 we'll get it as a total drop. So what is the 6 times, no, 6 by 2 pi, what is the drop due to that, because of the inductor, no, that is LdA by dt VL. So that is a LdA by dt notation. So that's why it is with respect to d omega t, then you represented omega and integrate this portion, you will get it as a 3 omega ls by pi into id. So you want, you can use the notation ls because source, well, load also having the inductor, that's why you are maybe getting confusion, that you can make use of s here. Then ls 3 omega ls by pi into id, and then your final expression of average actual voltage minus drop 3 omega ls by pi into id. And if it is a with overlap period, same in the case of single phase also what we use, 2 Vm by pi into cos of alpha plus mu means it is a plus omega ls by pi into id. That same fashion use of alpha plus mu to find the overlap angle, all these things you can make use of cos of alpha plus mu, instead of minus you will put it as a plus here. So that is a p pulse converter or a m pulse converter, the drop will be, this is the generalized expression, omega or m by 2 into omega ls by pi into id. So this is the small expression. It is also very important if the question is asked to explain the effect of source inductance, if not mentioned whether it is a 3 pulse converter or a 6, I mean single phase converter or a 3 phase converter, you can take your choice, anything you can write and you derive the expression, that is the, and they may ask the problems also related to overlap angle, or average output voltage or inductor value, all these things. We'll see some problems also in this. And now 3-phase problems. 3-phase full converter feeds power to the resistive load of 5 ohms for a firing angle of 30 degrees. So the load takes 8 kilowatts. An inductor of large value is also connected to the load, that means it is a RL load, to make the current ripple free, that is a continuous current. If it is ripple free, they mention there is a large inductor, obviously it is a continuous current mode of operation. Find the value of per phase input voltage. So now we can see here the question, they asked as a voltage per phase. Supply voltage is not given, but the load is given, current is given, all the things is mentioned, and you have to find the per phase voltage. Now first you find the load current, because voltage is given, resistance is, I mean power is given, as well as the resistance is given, we can easily get the current, because current, I mean power formula P is equal to I square R, and I don't know what is the load current, but load resistor is given, and just you can find the power is 8 kilowatts. So then current is equal to 8 kilowatts by 5 root. So that will give as a 40 amperes. So now this is the current. But according to our 3-phase full converter, what is our expression? VDC expression, you can see that 3 root 3 Vm by pi into cos alpha. This is the phase voltage we have to represent. So that's the reason what we'll do is 3 into root 2 into root 3. This is a line by root 3 by pi into cos alpha. This way also I can write whatever. So here actually we will need to use the phase voltage. So that's why line voltage is known to you, then you divide it by this. Then what, some cases this will get cancelled. And then you can use directly 3 Vm by pi into cos alpha, because Vm is root 2 into Vs. No, that's why. So this formula also correct. Anything is same. In that you can see that 3 root 3 Vm by pi into cos alpha is general expression. But some books they represented 3 Vm by pi into cos alpha also, because the root 3 will get cancelled out. In that case it is a phase voltage directly. So now we can see that to convert into phase voltage, I made it as a by root 3, and here root 3 will get cancelled. Now we know the average voltage. So what is current expression? As you know that current is equal to VDC by R. Now I know what is the VDC. This is the formula by R. R value also known. Then I naught also known. In that expression, unknown parameter is a Vm. See that? So you just find the Vm first. Once if you know Vm, they are asking as a phase voltage. Then according to this, we can write Vm by root 2 into root 3. So that will give as a phase voltage. So this is the small thing. Same whatever problems you want to use, any same problem, we make use of changing the controller. Suppose if this controller single phase also you can use it. In that case, you can make use of find the Vm. That is also sufficient. So like that, R three phase full converter is replaced by three phase semi converter. Your average expression only going to change. So that way we can able to do that. And now another problem you can see that a three phase semi converter. Now converter is a semi converter. Is feeding input is a 400 volts 3 phase 50 Hz supply, and the average output voltage is 50% of maximum possible output voltage. What is the condition is mentioned here. Same problem, you make use of single phase semi converter also, or single phase full converter also, you try to solve it. Once if you know this very simple logic, what they are asking is semi converter. First thing is they mention as a semi converter, and then input is given, supply voltage is given 400 volts and 50 H. Output also given, V out or VDC. What is the value is given? 50% of VDC maximum. That is the VDC. And now load resistance also mentioned. That is a 12 ohms. So suppose determine firing angle. Let us assume that first bit is alpha. Then how will you find the firing angle? Once if you know VDC, this value, and already they given in the problem something maximum into some alpha, let it be. This is the unknown parameter. Then what is VDC is known to you, this value is known to you, only unknown is alpha, you will get it alpha directly. But how the VDC value you have to calculate? Directly VDC is not given, only 50% of maximum is our VDC. Under that condition, what is the alpha? How will you get the VDC maximum? This is the question. Once if you know this VDC maximum, you can easily solve that problem. At what condition you will get the VDC maximum? Anybody? At alpha is equal to 0. Any controller at alpha is equal to 0, you will get it as a maximum expression. Now you know normal VDC expression, there you put it alpha is equal to 0, that is nothing but a VDC maximum. Over. So that is different questions they ask. Firing angle, average output current, RMS output current and voltage, average and RMS thyristor currents, efficiency, transformer utilization factor, power factor, all these things is required. So now as you know that this is our expression, because it is a three-phase semi-converter. VDC is nothing but a 3 root 3 Vm by 2 pi into 1 plus cos alpha. Now I want VDC maximum. How will you get? Put it 3 into root 3 into Vm root 2 into 400 by root 3 into 1 plus cos 0. If you solve this, you will get it as a VDC maximum. Some voltage let it be. And then actual VDC is equal to 50% of VDC maximum. Then now I know VDC also. First bit I want to find what is the firing angle. This one. How will you get the firing angle? Again use the same formula. VDC is equal to 3 root 3 Vm by 2 pi into 1 plus cos alpha. Then I know VDC from where? This one. Whatever VDC maximum value you are getting, suppose if it is a 400, let us assume that, or maybe 308, anything, some value, I will show that value also, into 0.5, that is your VDC. You can put it here, 0.5 into VDC maximum, that is equal to this value into 1 plus cos alpha. And output is a cos unknown is cos alpha, and from that alpha is equal to cos inverse of that will give as a first bit over. That is the way we have to solve it. Now we can see that alpha is maximum, then 3 root 3 Vm by 2 pi into 1 plus cos alpha. Cos 0 is 1, so therefore 1 plus 1, 2 will get cancelled out. We'll get it as a 3 root 3. What is Vm? Root 2 into 400 is given, that is a line voltage is given. Suppose directly is mentioned as a phase voltage, no need to use as a root 3, because in our problem is given supply voltage is 400 volts, that is a line volts. So then that is what line, because in our formula is a phase here. That's why line voltage is given. Line voltage divided by root 3 will give as a phase voltage. Then root 2 into 400 by root 3, root 3 will get cancelled out. Is just to calculate this, we'll get it as a 540.189. This is the VDC maximum. That is not a actual VDC, that is a VDC maximum. Once if you know VDC maximum, then this is a VDC maximum. Then I will get VDC, that is a 0.5 into 540.189. That will give as a VDC. That is equal to 270.0954. So this is the case of VDC. Indirectly is given this value, and they are asking alpha. So will you get alpha? Again same expression you can use it. VDC is known now, only unknown parameter is alpha. Then use this formula. Here this value is now 270.0945. As usual, this plus 1 plus cos alpha. That's all. So only cos alpha is unknown. That is same formula, because now VDC is 270 point this plus this into 1 plus cos alpha. Cos alpha is equal to something, will get alpha is equal to cos inverse of that. So that is the case of alpha. Now we got it, alpha is equal to 90 degrees. That is the first bit. And second bit, average output current. So once if you know the voltage, and you can easily find the average output current, because the IDC VDC by R. R also mentioned in the problem. VDC is 270.0945. We already calculated that. Divided by R value is 12. Then we'll get it as a second bit. And then RMS output voltage. So RMS output voltage expression VRMS. So once if you know the VDC and the limits, just square it 12 power 1 by 2. If you solve that, we'll get it as a VRMS under this condition. Again, we can simple substitution, see that Vm is known to you, 400 by root 3 into root 2, numerator root 2 into 400 by root 3. That is a Vm. And then you have all these parameters are known to you. You can substitute, you will get it as a, what is the value of VRMS. So then RMS value of output current. So this divided by R will give as a RMS value of the output current. That is nothing but a 28.86. Then average thyristor current. So here we derived that expression in the while I'm explaining theory part, RMS and average thyristor currents. So not a total current. So each thyristor is conducting how many degrees, and based on that you'll get it as a average thyristor current. So that is a IDC by 3, then you can get it as a average thyristor current. Similarly RMS by root 3, that will give as a IRMS value already calculated, and by root 3 if we give, then we will get it as a RMS value of the thyristor current. So this is the average thyristor current, this is a RMS thyristor current. And then rectifier efficiency. So efficiency of a converter, like we calculated single phase, no, like that, output, that is a PDC by PAC. PAC is nothing but VRMS into IRMS. PDC is nothing but VDC into IDC. So if we do that, we'll get it as a what is the efficiency? PDC into IDC by VRMS into IRMS, and that will give as a efficiency. Now we got 60.7, and then there is a each thyristor conducts 120 degrees, as I mentioned, because this is a semi converter or a full converter, anything. The pair of devices are different. This is the output, let alpha is equal to 0 instant. This pair of the device, either it is a 6, 1, 1, 2, 2, 3 and so on, this will conduct 60 degrees. But what they mention, each thyristor. So each thyristor means any one full cycle, if I take it, one is conducting here and here. This is 60 degrees, here is 60 degrees. That means 120 degrees. Or 2 here and here, 3 here and here. That means 60 and 60. Each device is conducting 120 degrees. That's what the formula. Here you can see that RMS value of input current, because input is coming from whenever the device is conducting. That's why input current is equal total 120 degrees in that period. So this is the formula. This also I given in the previous slides. There is RMS value of input current and volt amperes in the input side. That also can mention this value 3 into Vm. This Vm is equal to by root 3, I mean phase voltage, and then transformer utilization factor PDC by volt amperes. So same as the single phase notation only, and we'll get it as a transformer utilization factor. After that, power output IRMS square into R or VRMS square by R, anything you can use it. This will give as a power output. Then there is a input is equal to output, because let us assume that losses are neglected. So that case we'll get it as a power input is equal to power output, that will give as a power factor. You can see that power input is equal to output VRMS into IRMS. So that will give, I mean input is equal to output case into cos phi. This is the power expression, and cos phi is equal to this one. So that will give as a power factor. Now we'll see another problem. A three-phase fully controlled bridge converter is connected to three-phase AC supply. Now the AC supply value is 440 volts. So this is a 440 volts 50H, and alpha is given pi by 4, and current is maintained constant 9 amperes. That means ID or I naught is given, that is a 9 amperes, and Vs 440 volts, and load voltage, that is VDC, that is 360 volts. Then determine, this problem is related to overlap problem. So now determine what is the source inductance, load resistance, overlap period. So to get source inductance, direct formulas we have to use it. VDC, this is equal to 3 root 3 Vm by pi into cos alpha minus 3 omega Ls by pi into Id. Now VDC is known to you, this also known to you, and alpha is given and what is unknown. So in that minus factor 3 omega ls by pi into id. What is first bit? ls. ls only unknown. id is known and omega is known 2 pi f. Then directly you'll get it as a what is the ls. So that is the first bit. You can see that as usual formula 3 root 3 by pi or Vm by pi into cos alpha and minus 3 omega ls by pi into id, and all the this is not into, it is equal to Vdc is equal to, you can see here is equal, Vdc is equal to 3 root 3 Vm by pi into cos alpha, and now substitute the value. This separately can directly can use it. Root 2 into line voltage by root 3. This is the Vm phase. Always in all the 3-phase problems, wherever you want to do that Vm, if the problem is given line voltage, then automatically root 2 into VL by root 3. This is the Vm case. Suppose they mention in a problem the voltage per phase. Under that condition, we can use Vm is equal to root 2 into phase voltage. So this is in that case by root 3 don't use it. So that you must take care, otherwise all your answers will get wrong. If you not divided by root 3 or if you divided root 3 unwantedly, so all the cases, all other sub problems will get wrong answers. So that's why you take care of this. If it is given line to line voltage, then root 2 by root 3 you have to use. And as usual, you substitute 360 is mentioned in a problem EDC, and that is equal to this alpha is pi by 4 and 3 omega 2 pi f, you can use as a 2 pi f ls into 9 by pi. 9 is a id, and we'll get it as a ls value, that is 22.29 millihenry. And load resistance, that is a second bit. So will you get the load resistance? Once if you know the voltage and then current, you can easily get as a resistance. So VDC is known and ID also known, 9 I think it is given, ID value, and VDC value is 360, then you can get it as a, what is the R value, 360 by 9. And another one, overlap angle. So will you get the overlap angle? So overlap angle is nothing but a same formula, you can use it, but make use of a plus. So VDC is equal to 3 root 3 Vm by pi into cos of alpha plus mu plus 3 omega ls by pi into id. So now what is unknown? I know VDC, this parameter is known, alpha is known, only unknown parameter is mu, and ls also known, and because from the first bit ls we calculated, no, use the same ls here, and id is given 9, and we will get cos of alpha plus mu is equal to something, then alpha plus mu is equal to cos inverse of that, then mu is equal to that value minus alpha. So that will give as a overlap period. So there is a this type of problems are very important. Either it may be single phase or a 3-phase. Only thing is the problem is same. They may be mentioned the supply voltage different, and instead of 3-phase full controller, they may use single phase full controller. Then remaining parameter, whether it is ls or r or mu, all the things are same. So in that case, we have to use the formulas based on your controller, whether it is a single phase controller or a 3-phase controller. If it is a single phase controller, 2 Vm by pi into cos alpha minus omega ls by pi into id. And similarly, id expression, all these things are there. Anything, it depends on your available data, you can choose the formula. But only 3 formulas there: VDC, in terms of cos alpha alone, minus you can use it, in terms of alpha plus mu you can use it plus drop, and another one is id expression also you can use it if required. Now this is the same formula, just make use of a plus here, and you will get it as a cos of alpha plus mu is equal to something, then you will get it as a alpha is equal to. So this is the mu is equal to 14.69. So the thing is, the mu value, if it is increases, your average output voltage is going to be decreases based on your inductor value. If source is having large inductor, it store more energy, so it will dissipate, it will take more time, current will be gradually decreases, and during that your drop will be more. So that is the reason you can get variable voltage if you change the inductor value. And same another problem, you can see that three phase full converter supply 400 volts 58, load current is continuous and negligible ripple, average current is 10 amperes, and the inductor value so 0.5 millihenry. Determine the overlap angle when alpha is equal to 30 degrees. So here they ask directly as a mu value. So if mu value is required, then first of all what we need is average output voltage. Once if you know the average output voltage, and you will get it as a mu value. So for that we can see that there is average expression as usual VDC. And now in some problems if they mention source having some resistance, that R value also mentioned, that is the source resistance is some 1 ohm or something like that is mentioned, this formula must be RS into ID. And the same problem if VT is given 1.5 volt minus VT, all these things you must consider, otherwise the total answer will get wrong. This it is very simple notation. This is due to the source inductance, this is due to the source resistance, this is by considering a voltage drop across the device when the device is a conducting mode of operation. So all these parameters you must consider, and in this that data is not given, that's why we not subtracted as a minus parameter. And now we can see that I want to know EDC. So therefore 3 into root 3 by pi. So Vm, how will you get it? It is just a minute. This is not a by 2 pi. This is a by pi here, because it is a full controller only. Full controller 3 root 3 Vm by pi, not a 2 pi. So now for Vm is given as a 400 now. So then 400 into root 2 by root 3 cos 30, alpha is mentioned 30 degrees, and minus 3 omega, this also change it, omega is 2 pi into pi, this is not 20, 2 into pi, 2 pi, f 50, and L that is a 0.5 millihenry, and then ID that is a 10 by pi. So this is the substitution if you do that, and you can see that we'll get VDC 466.318. Once if you know the VDC, as usual, you can easily calculate the mu overlap angle. So using this formula, now VDC is known to you. This parameter is known. Only unknown parameter is mu. Alpha also known, because in the previous problem itself we have the alpha value 30 degrees. That's why alpha is known. And here whenever if you use cos of alpha plus mu, you must use 3 omega Ls by pi into ID, and you will get it as a mu value. So this is mu is 0.678, and this is the today's class. If I have any doubt, you can ask me. So some of your classmates not yet submitted the assignment still. Before 5 o'clock, if you not submit, I will put 0 and submit it to department. That is your final marks. Only 45 students, 45 members only submitted out of 62.